Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the concept illustration problems which are based on the magnetic field due to a straight current carrying wire. You can see that there are two infinitely long current carrying wires carrying the same current in the direction as shown, and there is a point x comma y. We have to find out the net magnetic field at this point. You can see by using Fleming's right hand rule, screw rule, you can see that the magnetic field due to this wire at this point is inside the plane of the paper. You can use the Fleming's right hand rule that magnetic field is inside the plane of the paper. It would be circulating like that and it would be going inside the plane, and the magnetic field due to this wire at this point will be outside the plane of the paper. Okay, you can use the Fleming's right hand screw rule which we studied in the previous video. So first of all, let us find out the magnetic field due to this single wire. Now you can see that this wire is having infinite length from both the sides, and therefore phi 1 is equal to phi 2 is equal to 90 degree for this wire, and the perpendicular distance of this point from this wire is you can see that it is x, and the perpendicular distance of this point from this wire is y. So the magnetic field due to wire 1, let us name that this wire is 1. So wire 1 has a magnetic field of mu naught I by 2 pi a, in fact 4 pi a sin 90 plus sin 90. Sin 90 plus sin 90 will be 2, and therefore the final formula will be mu naught I upon 2 pi a. Now a for this wire is x, and the direction of magnetic field is cross, which is going inside the plane of the paper. Now if we name the wire along x-axis as wire 2, then B2 will be equal to mu naught I by 2 pi y. Again, the angles for this wire will be 90 and 90. Okay, and the direction will be outside the plane. Depending on the fact that whether x is greater or y is greater, the net magnetic field will have its direction, net direction. But let us imagine that x is less than y, and therefore B1 is greater than V2. So the net magnetic field is mu naught I upon 2 pi 1 upon x minus 1 upon y, and the direction will be inside the plane of the paper. Okay, because I have assumed that the net magnetic field is due to the greater value of B1 and due to the less value of B2. Now we move on the next question. In this question, you can see that there is a point, this point, and there are two wires which are of infinite length but from only one side. So this wire, which is along y-axis, is coming from infinity, and it is transferring the current to this wire which is going to infinity. We have to find out the net magnetic field at this point. Now again, let us name this wire as 1 and let us name this wire as 2, and you can see that this wire has the magnetic field at this point in outward direction. The magnetic field of wire 1 at this point is pointing outside the plane, and the magnetic field of wire 2 at this point is also pointing outside the plane. So the net magnetic field will be the sum of these two magnetic fields. And first of all, let us find out the magnetic field due to the wire 1. To find out to find out that magnetic field, we have to draw perpendicular from the wire to this point, and this distance is x. And we have to join the two ends of the wire from this point. The one end is this one and the other end is at infinity. So this angle would be 90 and this angle is, let's suppose, alpha. So the B1 magnetic field due to wire 1 will be mu naught I by 4 pi x sine 90 plus sine alpha, and sine alpha will be equal to perpendicular upon hypotenuse. Perpendicular is y, hypotenuse is r. So y upon r is under root of x square plus y square. And this magnetic field is pointing outside the plane. So B1 will be equal to mu naught I by 4 pi x, sine 90 is 1 and sine alpha is y upon under root of y square plus x square. Now B2. B2 is the magnetic field due to the other wire, and you can first of all draw the perpendicular. The perpendicular distance of this wire, second wire, from this point is y. You can see this angle is beta and this angle is 90. So again the B2 will be mu naught I by 4 pi y, and this is 1, sine 90 is 1 plus sine beta. Sine beta will be this perpendicular distance upon this. So sine beta will be x upon r. So it would be x upon under root of y square plus x square. So the net magnetic field will be B1 plus B2. So it would be mu naught I by 4 pi, and this is 1 by x plus y by x under root x square plus y square plus 1 by y plus x by y under root of y square plus x square. So this is the net magnetic field due to this system at point P. Now let us move on the next question. In this question, you can see that there is a cyclic cyclic polygon, and this is a four-sided polygon, regular polygon, which is also a square, and this is a cyclic three-sided polygon, which is also a triangle, equilateral triangle. So we have to find out the magnetic field at the center, geometrical centers of these two figures, and it is given that current is flowing through the complete frame, which is I. The side of each side, the length of each side is A, and what we have to do is to find out the magnetic field at O. So what we should do, we should see that if we rotate our fingers of our right hand in the cyclic order along with the current like that, anti-clockwise, then you can see that your thumb will be pointing outside this plane. You can rotate your fingers of the right hand and you can observe that your thumb will be pointing outside the plane. So we can conclude that if current is following the cyclic order, then in all the wires, then the magnetic field at the geometrical center would be in the same direction due to all the wires. So individually also you can check that the magnetic field due to this wire is outside the plane at this point. The magnetic field due to this wire is outside the plane at this point. The magnetic field due to this wire is outside the plane at this point, and the magnetic field due to this wire is outside the plane at this point. Now what we can do, we can find out the net magnetic field by multiplying the magnetic field of one wire with 4. So the magnetic field of any one wire will be B, and B will be mu naught I by 4 pi A. Now A is the perpendicular distance, which is A by 2 in this case, and this angle is phi 1 and phi 2, and it is equal to 45. So it would be sine 45 into 2. So you can see that B will be equal to mu naught I by root 2 pi A. Okay, and the direction of B will be outside the plane. Dot represents outward direction. Now this root 2 can be seen by cancelling this 2 with 4 and this 2 with 4. So there is a 1 by root 2 term due to sine 45, and therefore the net magnetic field due to this square can be written as 4 times of B, and 4 times of B will be 2 root 2 mu naught I by pi A. Okay, and now let us find out the magnetic field due to this triangular frame. Again, what we'll do, that we'll find out the magnetic field of one wire and we'll multiply it with 3. Now again, if you rotate your fingers in the direction of current, which is clockwise in this case, then you can easily see that your thumb will be pointing inside the plane of the screen, and therefore the magnetic field will be pointing inside the plane. And if you find the magnetic field direction due to individual wires at the point O, then you can also observe that the magnetic field direction at point O due to individual wires is also inside the plane, and hence the magnetic field due to all the 3 wires will add up. Okay, so what we'll do, we'll find out the magnetic field due to a single wire. So let us suppose that this wire is creating some magnetic field at this point, which is B, and B, this angle phi 1 phi 2, these are two phi 1 phi 2s. So this is 30 degree and this is 60 degree because it is an equilateral triangle. So this distance we know is A by 2 root 3. So B is mu naught I by 4 pi A by 2 root 3 and into 2 sine 60. So B will be equal to, this is 2 and this is 2 cancelled, and B will be, sine 60 is root 3 by 2, so it would be 3 by 3 mu naught I by 2 pi A. Okay, because sine 60 is root 3 by 2, and that root 3 and that root 3 becomes 3, and that 2 is this 2. So this is the magnetic field due to one wire, and the net magnetic field due to the complete triangular frame B net will be equal to thrice of B. So it is 9 times of mu naught I by 2 pi A, and the direction will be pointing inside the plane. Okay, so this is the net magnetic field due to this triangular frame. Now let us move on the next question. In this question, you can see that it is a wire which is infinitely long from one end, and it is making a V shape with another similar wire which is also infinitely long from one end. Now we have to find out the magnetic field at a point P, which is at a distance of D from the apex of these two wires, and these two angles are 30-30. The current is going like that and this is flowing like that. So first of all, let us find out the magnetic field direction. So by using your right hand and by using Fleming's right hand screw rule, you can see that the magnetic field direction due to this wire, due to this first wire at this point, is inside the plane of the paper, and due to the second wire at this point is also inside the plane of the paper. So what we have to do, we have to find out the magnetic field due to a single wire, and then we will add up the magnetic fields due to both the wires. So let us draw the diagram for a single wire. This angle is 30, this point is P. So first of all, we have to draw the perpendicular from the wire to point P, and this distance is D. Now A, which is the perpendicular distance, is D sine 30, and D sine 30 is D by 2, and we have to join the point P with both ends of the wire. So by joining the point P to this one end, you can say that this angle phi 1 is 60 degree, and by joining the end P with the other infinite end, then you can say that this angle is 90 degree. So B will be equal to mu naught I by 4 pi A, and A is D by 2, and one angle is 60, so it is sine 60, and the other angle is equal to sine 90. So this will be the magnetic field due to single wire. So B will be equal to mu naught I by 2 pi d. Sine 60 is root 3 by 2 and sine 90 is 1. So it would be equal to mu naught I by 4 pi d root 3 plus 2. This is B. And the net magnetic field will be B net will be equal to twice of B, and twice of B will be equal to mu naught I by 2 pi d into root 3 plus 2. And the direction, we have already seen that direction will be inside the plane of the paper, which is represented by a cross. Now let us move on the next question. In this question you can see that there is a star shaped of wires, and we have to find out the magnetic field at the geometrical center of the figure. You can it is given that the side of each of this arm is A and a current of I is flowing through the figure. Now if we'll find out the magnetic field due to this single wire at this point, then it is quite tough part, but you can also apply a simple analogy that we can imagine this figure to be formed as the combination of two triangles, which is equilateral triangles, and we have removed this hexagon from this triangle, combination of triangles. So this figure will be formed. So obviously if we are assuming the equilateral triangle, then you can see that the magnetic field due to both of the equilateral triangles will be outside the plane, and therefore we can see that, let us use another page. We can find out the magnetic field due to both the triangles. This is the first triangle, and I'm writing the magnetic field due to the first one, and the direction of magnetic field is outside the plane because current is in anti-clockwise sense, like that. The side of this triangle is 3A. You can see that side is 3A. So this is 3A and this is 3A. This is 3A. Now we can easily find out the magnetic field due to this triangle. So B of one triangle will be equal to mu naught I by 4 pi d. D is perpendicular distance. This distance will be 3a by 2 root 3. So this will be root 3 by 2a. Okay, so this will be root 3a by 2, and this angle is 60, phi 1, and this angle is 60. So this will be 2 sine 60, and this is the magnetic field due to only one wire. So to find out the magnetic field due to the complete triangle, we should multiply it with 3. So B of this triangle will be equal to this is 2 and this is cancelled. So sine 60 is root 3 by 2, and therefore root 3 and root 3 will be cancelled out. So net magnetic field will be equal to 3 by 2 mu naught I by pi a. This is due to the triangle. Now we know that there are two triangles, so we will find out the net magnetic field by adding up the magnetic fields of two triangles and subtracting the magnetic field of the hexagon. So now let us find out the magnetic field of hexagon. So I'll draw the hexagon. This is hexagon, and in this hexagon you can see that each side of the hexagon is A, like that, and the magnetic field at this point can be calculated by finding out the magnetic field due to one wire and multiplying it with 6. So B due to hexagon will be equal to 6 times of B of one wire, and B of one wire will be equal to mu naught I by 4 pi A. Now this side is A and this is 60, and therefore this D will be equal to this is also A. D will be equal to A cos 30, which is A into root 3 by 2. This distance will be root 3 A by 2, and these two angles phi 1 phi 2 will be equal to 30, so it would be 2 sine 30. The direction will be outside the plane only, and B will be equal to mu naught I by 2 root 3 pi A, and the net B due to hexagon, B net due to hexagon will be equal to 6 times of B, so it would be equal to 6 mu naught I by 2 root 3 pi A, and it would be equal to root 3 mu naught I by pi A. So now the net magnetic field will be twice of magnetic field of the triangle minus magnetic field of hexagon. So B net will be equal to twice of B triangle. B triangle was 3 by 2 mu naught I by pi A. So it is 3 by 2 mu naught I by pi A minus B of hexagon is root 3 mu naught I by pi A. So this will be equal to root 3 mu naught I by pi A, and this is root 3 minus 1. So the direction will be outside the plane. Okay, you can see the direction because current is flowing in anticlockwise sense. So this will be the net magnetic field. Now let's move on the next question. In this question, you can see that this is a figure which has wires arranged like that till infinity, and each of this arm has a length of A like that. This angle is 30, this angle is 30. We have to find out the net magnetic field at point O. Now we know that the magnetic field due to all of these wires which are having this point O on its axis will be 0, because these wires, there is another wire, this one, it is having this current. So the magnetic field will be 0 due to these wires which is having this point O on its axis. We know that the magnetic field on the axis of the wire is 0, and the magnetic field due to this first wire will be equal to B will be equal to the direction is inside the plane, you can see. Let us write down net B. So net B will be equal to the B due to this first wire which is having the direction inside the plane. So B will be mu naught I by 4 pi D. Now D is A cos 30. So A cos 30, and the two angles are 30, so it would be 2 sine 30 minus the magnetic field due to this wire will be outside the plane, and the only difference is the difference of A, which is 2A in this case. So it would be mu naught I into 2 sine 30 divided by 4 pi into 2A cos 30. And again the magnetic field due to this wire is inside the plane. The difference is 3A. So mu naught I into 2 sine 30 upon 4 pi into 3A into cos 30, and this goes to infinity. Now if we take common terms out, then b net will be equal to mu naught I. Now 2 sin 30 is itself 1, and here 4 pi cos 30 a. So in the denominator it would be 4 pi a cos 30 is root 3 by 2. Okay, and here it would be 1 minus 1 by 2 plus 1 by 3, 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus 1 by 5, and so on till infinity. So it would be b mu naught I by 2 root 3 pi a, and is the sum of these numbers 1 minus 1 by 2 plus 1 by 3 minus 1 by 4, and it is the series of log 2 expansion. So we can write it down as ln 2. So b will be equal to mu naught I ln 2 by 2 root 3 pi a. And the direction will be, obviously the biggest magnetic field is due to wire 1. So the direction will be inside the plane of the paper, cross. So this is the net magnetic field. Now let's move on the next question. In this question you can see that there are two wires, one is like that and other is like that, and current is flowing in this sense. So we have to find out the magnetic field at this point. We know that if we name this wire as 1 and this wire as 2, then we know that the magnetic field due to 1 will be 0, because this point is lying on the axis of this wire, and the magnetic field due to 2 can be calculated by extending this wire. This angle is 30 and this is perpendicular distance A. In fact, let us name it as D. So D will be, this is 60, so D will be equal to A cos 60. And if we connect this point with this end of the wire, and if we connect this point with other end of the wire like that, then one angle is 60 and other angle is 90. Okay, now B due to this wire will be equal to mu naught I by 4 pi D, which is A cos 60. And you should remember the special case in which I told that if this point is if the phi 1 phi 2 are both on one side of the perpendicular, so you can see that this is perpendicular and phi 1 is also on this side of the perpendicular and phi 2 is also on this side, then there is a negative sign in between sin phi 1 and sin phi 2, and obviously bigger sign will be bigger sin theta at bigger angle minus sin theta at a smaller angle. So bigger angle is sin 90, so it would be sin 90 minus sin 60. Okay, so B will be equal to mu naught I by 2 pi A, because cos 60 is half and sin 90 is 1 minus sin 60 is root 3 by 2. This will be the net magnetic field, and the direction of this magnetic field will be inside the plane of the screen. You can check by Fleming's right hand rule. Now let's move on the next question. In this question you can see that there is a circle, or there is a circular wire which is having these two wires connected, which are infinitely long wires, and these wires are having the current, and this current enters from this point and gets divided into two parts, and then it again combines and becomes the original current and goes to infinity like that. We have to find out the magnetic field at O, which is the center of the circle. So first of all, the magnetic field due to this infinitely long wire is 0, because this point is lying on the axis of the wire, And in the same way, the magnetic field due to this infinitely long wire will be 0 because the point is lying on the axis of the wire. Okay, so we have to find out the magnetic field due to these two wires. So let us suppose that current I1 is flowing from the upper part and I2 is flowing from the lower part. Now let us see that if the length of upper part is L1 and the length of lower part is L2, then we can say that I1 by I2 current will be divided in the inverse ratio of resistance R2 by R1. And resistance is obviously rho L by A, rho and A is same, so R2 by R1 will be L2 by L1. And arc length is theta into radius, so radius is same, so L2 by L1 will be theta upon this angle is 2 pi minus theta. So we can say that I1 into 2 pi minus theta is equal to I2 into theta. Okay, now the magnetic field due to the upper circle, I'll be telling you that due to a circular arc, due to this circular arc, the magnetic field is, if this angle is theta, so the magnetic field is mu naught I by 2r into theta by 2 pi. I'll be telling you, I'll be deriving this expression in the later part, but this is an important question, so I am taking it here. So B due to the lower part of the wire will be B2, and it would be mu naught I2 by 2r into theta by 2 pi, and the direction of magnetic field due to lower part is outside the plane of the paper, and B1 will be in the inward direction, and it would be mu naught I1 by 2r into 2 pi minus theta by 2 pi. Direction will be in the inward direction. So you can see that both magnetic fields are pointing against each other in the opposite direction, and I2 into theta and I1 into 2 pi minus theta is same. So the net magnetic field will be B2 minus B1, and as we know that B2 is equal to B1, so the net magnetic field will be 0. So this is a very important law in these kind of questions, that if current has to divide on its own, then the net magnetic field will be cancelled out. You can also see that in this case the current flowing through this wire will be let us see that the resistance of these three is 3R and resistance of the lower wire is R. So current flowing from the lower wire is I1 and from upper is I2. So I1 will be equal to 3I by 4 and I2 will be equal to I by 4. This can be found by current division rule, that I1 plus I2 is equal to I, as well as I1 by I2 will be divided in the ratio, inverse ratio of resistance 3:1. So you can conclude that I1 will be 3I by 4 and I2 will be I by 4. So the magnetic field of this one wire is B1, and B1 will be equal to whatsoever. Let us suppose that it is B. But you should know that in the formula of B we have substituted the value of I1, which is 3I by 4, and in the formula of B2 we have B2 is the magnetic field due to all these three wires, and you can see that the magnetic field of the upper three wires and magnetic field due to this lower wire will be against each other and opposite in direction. Therefore net magnetic field at the center will be opposing each other, and the magnetic field B2 due to the upper three wires will be also equal to B, due to the fact that the current flowing in them is 1/3, but they are three wires, so we'll be multiplying with 3, so there will be the same magnetic field as created by the lower wire. So the net magnetic field will be again 0. So what I'm trying to say, that if the current is dividing on itself in the ratio of resistance, then the net magnetic field at the geometrical center of the figure will definitely be 0. In the same way, if we will find out the net magnetic field at the center of this cube, then it would be 0 due to symmetrical current distribution. This is 0 because we know that each and every object will try to remain in a stable equilibrium and with the minimum potential energy. Therefore, to keep its potential energy minimum, these figures are not creating any magnetic field, hence they will not interact in the magnetic field. Therefore, we can say that the net magnetic field of these symmetrical current distributions in the closed figure at the geometrical center will be 0. Thank you.